Hi, welcome to this video about the characteristic polynomial or characteristic equation for eigenvectors and eigenvalues and eigenspaces. So in this video, we're going to be talking about what all that terminology means. We're going to talk about how you can find eigenvalues and use them to determine eigenvectors, and then also how you can define the eigenspace based off of your eigenvectors. So let's begin with a definition. So definition 14 states the characteristic polynomial that's a long phrase for today of n by n matrix A is the determinant of xi minus a. The equation where you have the characteristic polynomial equal to 0 is called the characteristic equation. Another big long phrase to be defined. There we go. So the characteristic polynomial is the determinant of xi minus a. And if you set that equal to 0, that's the characteristic equation. So this is useful because the characteristic equation is what we're going to use in order to find eigenvalues. So we're going to summarize that in theorem 29. Which states the following. Let A be an n by n matrix. And suppose the determinant and I'm going to use lambda I minus A is equal to 0 for some lambda in C. So we're now allowing complex values here, not just real. Then lambda is an eigenvalue. Of A, and there exists an X in Cn, so not just Rn, but Cn, so we're allowing complex entries here, which is non-zero, not the zero vector, so that Ax is lambda x. In other words, what this theorem is doing is it is telling us how you can find eigenvalues and their associated eigenvectors. So I'll just remind you that this was our definition for eigenvalue and eigenvector. X is an eigenvector if when I multiply it by some matrix A, I get a scalar multiple of it. So this was our definition of eigenvectors and eigenvalues. And what this is doing is it's telling us we can find the eigenvalue by throwing it into here, right? Finding the characteristic polynomial and setting it equal to 0. So that's what we're going to do. We're going to do an example of finding some of the eigenvalues for a matrix. So let's do that. All right, so this is example 27. And we're going to let A equal a 3 by 3 matrix 5, 1, 0, 0, minus 7, 0, negative 3, 0, negative 2. And we're going to state the characteristic equation. And find the eigenvalues. Okay, so when we go to set this up, to state the characteristic equation, what we need to find is the determinant of xi minus a and set that equal to 0. This is our characteristic equation. So to determine that, we need to figure out what is xi and then subtract a from it. Now, as you go through this, the more of these you do, after a few of them, you'll just be able to, find it right away. But I'm going to write out all the steps to begin with. So because this is a 3 by 3, I'm going to take the 3 by 3 identity. And that's what I'm going to multiply by x. And then I subtract the matrix A. So in this case, when I multiply this by x, the only thing that's going to change is along the diagonal. So I'm just going to take a little shortcut here, writing it that way. Oh, look, I won tic-tac-toe. Yay. Okay, so then what we're going to do is we're going to take x minus 5 and then 0 minus whatever. So everything along the diagonal is going to end up with an x in it. And everything else is just going to change its sign because it's being subtracted from 0. So this is going to give us x minus 5. 0 minus 1 is a negative 1. 0 from 0 to 0. And we get a 0 here. X minus negative 7 is going to become x plus 7. And 0 minus 0 is 0. 0 minus negative 3 is positive 3. 0 minus 0 is 0. And then x minus negative 2 becomes x plus 2. So that's our first step. We're going to take xi and we're going to subtract our matrix A. So really the shortcut that you're going to develop over time, once you feel comfortable doing this, is you just do x minus everything along the diagonal. So x minus 5, x plus 7, x plus 2. And then everything else changes sign. So 1 became negative 1, negative 3 becomes 3. And that's it for this particular case because we had so many zeros. So after you do that, now you need the determinant of that beast. So to find the determinant, you're going to consult Professor Lenny over here. Not Lenny. Lenny says hello. So we're going to find the determinant. So we're going to set that up. X minus 5, negative 1, 0, 0, x plus 7, 0, 3, 0, and x plus 2. There we go. So you can find your determinant using, your preferred method of finding a determinant. In this case, I'm going to just use regular expansion along this last row because we have, don't get caught on my sweater boobs. There you go. Because we have some zeros here. So that's going to be helpful. Good. Okay. So remember, we've got plus, minus, plus, minus, plus. That's going to help me figure out the signs of all of these. So zeros, I don't care, but this one becomes a positive. So I'm going to get x plus 2. And then I get rid of that row and that column, and I have to find the determinant of this. So that's going to be x minus 5 times x plus 7. And then minus 0. So could have that in here, right? But you're subtracting 0, it's not going to change. So we don't really have to write that extra piece in there. Now for this one, we were asked to find the characteristic equation, not just the polynomial. So if I said, find the characteristic polynomial, it would be this polynomial here. Please do not multiply that out because our goal is going to be to set this equal to 0 and solve. So if you have something gorgeous and factored like this, that is a boon. It is a blessing. You want that. So don't multiply that out to get a cubic, because all you're going to have to do is factor it again. So we're going to take that, we're going to set that equal to 0. And this is our first part. That's our characteristic equation. Next, to find the eigenvalues, we just find solutions to this equation. So, and I'm just going to use lambda instead of x, because we usually represent them as lambdas. So from this factor of x plus 2, we're going to get that lambda is -2. From this factor of x minus 5, we're going to get that lambda is equal to 5. And then from x minus 7, we're going to get that lambda is equal to 7. And then traditionally, we're going to number these 1, 2, and 3. Now, it does not matter what order you, this should have been a +7 here. I don't know why I had minus. Sorry about that. So anyway, so when you number them, it doesn't matter what order you put them in. What we're going to do later when we find eigenvectors is we're going to have like lambda 1. So we're going to need to know which one was lambda 1. So we'll just make sure you identify that when you state those. All right, good. Okay, so next we have this note. This is note 1. And this is going to tell us how we find the eigenvalues and the eigenvectors moving forward. So to find the eigenvalues, first you're going to solve the characteristic equation, right? So that was pretty easy in the example we just did. It's not always so easy, so we'll do a couple of examples where it's tricky. Then for each of those eigenvalues, we're going to find the basic eigenvectors by finding the basic solutions to lambda I minus a times x equals 0. Basically, what that means, so back over here, we had this matrix when we did xi minus a. So if I wanted to find the eigenvectors for these eigenvalues here, I would take -2, plug that in, and then I would solve that as if it were a homogeneous system. That matrix, I would row reduce it and get the solutions. Then I have to repeat that for 5 and for -7. So we're going to do an example of that, don't worry, but that's the basic idea, is we're going to substitute in the eigenvalues one at a time and then find the solution to that homogeneous system. Then of course you always want to check to make sure your solutions are good. So check that ax is the same as lambda x for each of those eigenvectors. So let's do an example of doing just that. All righty. Okay, this is example 28. And for this example, we're going to find all the eigenvalues and all the eigenvectors for this new matrix A up here. So what I'm going to ask you to do, since we just did an example of finding eigenvalues by finding the characteristic equation, pause the video here and work through it. Make sure you can find the characteristic polynomial, set it equal to 0, and then solve that resulting polynomial equation. And if you get stuck or you want to check your answer, then you can unpause and my work will have magically appeared on the board. So take a moment and work through it before you continue. So pause here. You paused? Okay. Alrighty, how did you do? So I decided to stop partway through because I wanted to show you sort of a nice way to be able to solve this equation without having to rely on a calculator or, oh my goodness, Lenny hair is all over the place, or having to do any fancy trickery. So, well, we have to do fancy trickery, but so what I did was I did my determinant of xi minus a equals 0. That's our initial setup. And I kind of used my shortcut here. So x minus 3. So x minus 3, x, and x minus 3. That's my diagonal. And then I negated the signs of everything else. Then I found the determinant by expanding along this first column because I liked that 0 there. So I have x minus 3. And then this determinant was x squared minus 3x plus 1. So where this came from. That's a 0 there, so I don't have to worry about it. And then I have minus 1 because this is positive, negative, positive. So there's my minus 1. close those out. This will give me -3 plus x. So that's where this came from. So one of the things that I notice as I'm writing this out, I can rewrite that as x minus 3, right? So I have x minus 3 times x squared minus 3x plus 1 minus 1 times x minus 3 is equal to 0. Now, this is helpful to write it that way because I notice that I really have a factor of x minus 3 in both of these like giant terms. So I can factor that out. And then I'm going to be left with x squared minus 3x plus 1 minus 1 is equal to 0. So I can use that to my advantage to help me factor. And then this simplifies because 1 minus 1 is 0. So I get x minus 3, x squared minus 3x is equal to 0. And then I can factor just an x out of there. So that's going to give me x times x minus 3 times x minus 3. Oh, hey, and now we have a duplicate factor of x minus 3. So we get x times x minus 3 squared equals 0. Now, for reasons that are going to become important shortly, we're going to need to know the algebraic expression for this, not just the graph. So we are going to need to know that we have one factor of x, and then this factor of x minus 3 is a double factor. So just kind of keep that in your head somewhere that we're going to need to know this. So to find the eigenvalues, we're going to set each of these factors equal to 0. And when we do that, I'm going to get, I guess I'll throw these up here. Lambda 1 is going to equal 0 from this factor, and lambda 2 is going to be 3 from the second factor. Okay, so how did you do at finding your eigenvalues? Did you do all right? Did you get stuck? Do we need to review factoring and that sort of thing? Let me know. All right, trying to find a marker that's not going to pass out on me here. Hopefully this one will work. Okay, so we were also asked to find the eigenvectors. So here's how we find the eigenvectors. I'm going to start out with lambda 1 equaling 0. So what we're going to do is we're going to take this matrix here. That's why I like to write it for reference. And we put 0 in for all the x's. So 0 minus 3 is a -3. X is 0, so we'll get -3, 0, -1. -1, 1, and then -3 again. Then we're going to reduce row echelon form it. The reason we're going to do that is because you want to imagine or envision that this is the coefficient matrix of a homogeneous system. So to solve a homogeneous system, you row reduce, and then you have to figure out where your parameters are and stuff. So when we row reduced, I went ahead and did that earlier, and I got 1, 0, 0, 1, 0, 0, 0, 1, 0. Yep. So what this means for our homogeneous system of linear equations, I notice I have a pivot position here in the third column and in the first column. I don't have a pivot position in the second column, which means my second variable is now my pivot, or is my parameter. This value here just means that 1z equals 0. So z is going to be 0. And then this means that x plus t is 0. So x is going to be -t. So if I write this in terms of a matrix as a linear combination, I get -1, 1, 0, t, right? Nothing else. So this vector here, the vector attached to t, this is going to be our eigenvector. So I'm going to call that x1. I'm numbering it the same as I'm numbering the eigenvalue up above. And that's going to equal -1, 1, 0. So take a moment and repeat that process now for lambda 2 equaling 3. The only difference is before we plugged 0 in for x, here you're going to plug 3 in for x, and then you're going to follow the same process. So try that out and see if you can find the other eigenvector for this matrix. And then, so pause, and when you get it, unpause, and my answer will have magically appeared yet once again. All right, so how did you do? Did you find the eigenvector okay? So when I did my row reduction, I ended up with some fractions, but that's okay, which gave me this solution. So this time z was the parametric component to my solution. So that gave me this as my answer in the end. Now, traditionally, eigenvectors, or I guess it's nice to represent your eigenvectors using integer values as opposed to fractions or decimals. So we're able to do this because t can be literally any number. So you can have infinitely different many ways of expressing this. So what I like to do is I like to think that, okay, well, let's say t is 3, right? So if I'm going to do that, then each of these gets multiplied by 3. And I would have 1, -1, and 3. And then I could use a new parameter, say s, where s is 1/3 of t. Or I can just write 1/3 t here. Right, so whatever number you have, you can still plug in for t and get your solution. So what that means is this integer valued vector is going to be our eigenvector. So I'm going to say x2 is equal to this. Now in my class, if you put the one with the fractions, you're not going to get marked wrong for it. It's just this is nicer to work with, especially in the future once we start doing things with these more often. So the fractions are not wrong, but you can feel free to change it to integers if you prefer. All right, so now that we have this example, let's do a definition. I'm going to see if I can fit the definition over here because there's I don't want to erase this example yet. It's going to be relevant in a moment. So this is definition 15. Trying to find where the edge is, right around there. Okay, definition 15. So the multiplicity of an eigenvalue is the number of times it occurs as a root of the characteristic polynomial. So if you're familiar with this term multiplicity from algebra in the past, multiplicity is just how many times a root occurs. So if you have like x cubed times x minus 1, x cubed happens 3 times because of the cubed. X minus 1 happens once because there's no exponent on it. If you had x cubed times x minus 1 squared, then x cubed would still have multiplicity 3 because of the cubed. It happens 3 times. And now x minus 1 would have a multiplicity of 2 because it's squared, so it happens 2 times. So that's all that multiplicity is. So as kind of a follow-up example, example 29, let's state the multiplicity of each of these eigenvalues. So here, lambda equaling 0 has multiplicity 1, and lambda 2 equaling 3 has a multiplicity of 2. Where I got this from is from my characteristic polynomial or from my characteristic equation. The x is a factor 1 time, so that's why x, which corresponded to lambda 1 of 0, has a multiplicity of 1. And x minus 3 is the factor corresponding to the lambda value of 3, happened twice. So that's why it has a multiplicity of 2. So whatever the exponent is, assuming you've grouped everything properly, that's going to be the multiplicity. The reason I'm a little reluctant to talk about just, the exponent is because sometimes you might write your answer this way, and the exponent in each of these is 1, but the multiplicity is 2 because it happens twice. So just be a little bit, careful of that, be aware of it. Okay, so now the pièce de résistance of this whole video, what connects it to what we've been doing all week, is the eigenspace. So I'm going to erase the board, make room for a bigger definition, and we'll define the eigenspace, and then we'll do an example. Alrighty, so let's define eigenspace. This is definition 16, and we're going to let A be an n by n matrix. And let lambda be a real number. So lambda is an element of R. The eigenspace of A corresponding to lambda, which is written E sub lambda of A, is the set of all eigenvectors corresponding to lambda. Now, so far, the examples that we've seen have only had one eigenvector, but you can have more than one parametric solution, right? So you might have T and S in your solution to a homogeneous system. So in that case, you would have 2 base elements for your basis for your eigenspace, okay, in that instance. So we're going to do, we've got 2 examples in example 30 here, where we're going to determine the eigenspace for each matrix and state the eigenspace's dimension. So to begin with, let's work through A. So A is the matrix that we saw in the last example. So we had lambda 1 equaling 0, and x1 was equal to -1, 1, 0. And we had that lambda 2 was equal to 3, and x2, we saw we could get 1, -1, and 3. So if I'm going to state the eigenspace, then remember we could have any linear combination or any scalar multiple of each of these as an eigenvector. So the eigenspace for lambda 1 of A is going to be the span of this vector, -1, 1, 0. Similarly, for the second eigenvalue, an eigenvector, that's going to be the span of 1, -1, 3. Now, because each of these vectors is only one vector that's forming our basis here, each of these has a dimension of 1. So the dimension of E lambda 1A is going to be 1, as is the dimension of the eigenspace of the second eigenvalue. And there we go. That's going to be it. So for part B, I'm going to leave that as an exercise. So that's kind of a wrap-up practice problem to kind of review everything that we've been going through in this video. We have seen this matrix before. We did find the eigenvalues for this matrix, or sorry, we found the eigenvalues in example 27. So we have the eigenvalues for this. From that, you need to find each of the eigenvectors. And once you have your eigenvectors, then you can set up your eigenspace and their corresponding dimensions. So to wrap up this video, we have just one theorem to close on. So this is theorem 30. We ended with example 30. Why not end with theorem 30 as well? And here's what it says. It says if A is an n by n matrix, then the dimension of the eigenspace is less than or equal to m, where lambda is an eigenvalue, of A with multiplicity m. So if we look at what happened in this previous example, lambda 1 had a multiplicity of 1, and we can see that the dimension of the eigenspace was also 1. Meanwhile, lambda 2 had a multiplicity of 2. This was our double root, but its dimension was only 1. So the dimension of the eigenspace is less than or equal to the multiplicity. It can equal it, as we did with this first one, or it could be less than, as it was with the second one. All right, so that's going to wrap up this video for today. In fact, I'm going to wrap up the videos for this week. So yeah, I hope you have a wonderful day. And yeah, we'll see you next week for some more linear algebra. Yay! Bye.